Welcome back, everybody, to our course on memory device technology for AI/ML computing. So, I'm your instructor, Dr. Shubhadeep from the Electrical Engineering Department at IIT Hyderabad. So, today we are going to start a brand new module. This is our 7th one. We will shift gears a little bit here and begin to appreciate how memory storage and device technology has played a big role in ushering in the data-driven AI/ML computing regime. Now, since most of today's AI/ML computation is carried out by deep neural networks, we will see what deep neural networks are. We will first try to get a sense of what exactly these DNNs are. After that, we will look at why, even though DNNs are very exciting in principle, but in practice, they turn out to be very compute heavy and power hungry. We will break down the factors behind this, and eventually we will see that the root cause lies in the fundamental mismatch between software architecture of these deep neural networks and the hardware infrastructure, that is von Neumann computing, that we have in modern day computing systems. And that's what leads us to explore what is the focus of our course: brain-inspired hardware itself. Okay. So, since this is a little bit of a shift, let's take a quick pause and recap the motivation of running this course. The big motivation was that we are seeing a computing paradigm shift. We will discuss that more in the next slide, but we are seeing big changes from logic-centric to memory-centric or data-driven computing. But here is the catch. While the paradigm shift is happening in computing, the hardware infrastructure has not changed in a real fundamental way to accommodate this change. And that is why all the problems that we just discussed of heavy computation and power. And that is why in the first part of our course, roughly 8 weeks, we covered what is the current computing infrastructure, which is von Neumann architecture, especially from the lens of the memory unit. So we looked at memory hierarchy, the memory array architecture. Then we went into SRAMs, which form caches, DRAMs, which form the main memory, NAND flash, which is your main storage. And also we spent quite some time in electronic or emerging non-volatile memories, such as RRAMs, PC RAMs, and MRAMs, which can give us two key benefits. One is to bridge the big I/O bottleneck between main memory and your main storage. Also, we gave hints when we were looking at eNVMs becoming very useful elements in supporting low power computing for AI. So now, as we move on to the second part, we will take a systematic deep dive into this very important question, which we have thrown some hints at. Can these memory technologies be further augmented so that they just don't store data, but also support hardware for neuromorphic or brain-inspired computing? Because that is what we need if we want to make AI/ML algorithms truly low power and efficient. Okay, so let us proceed. I know we have already discussed the change in computing paradigms, but because we will emphasize more on data-driven computing from now on, let us try to do a very quick recap. So in early computing era, what we have discussed, roughly from 1970s to 2000, the workload was primarily deterministic in nature. The key focus was on solving differential equations, or what the example that I had given was in trying to do computer aided design. Okay, so you had computational fluid dynamics, finite element analysis, and many such simulations which were primarily deterministic in nature. Here, the key bottleneck was clearly between the interface of the CPU subsystem and DRAM, or your main memory. See, we studied DRAM and we saw how we are trying to bridge this gap. And this is what we called the memory wall. And this was the era of compute-centric paradigm. But in the 21st century, the workload has shifted quite drastically. Today, it's not only about solving these equations, but more about how do you handle these large amounts of data which are available and make heuristic classifications to segregate this large amount of unstructured data into useful classes. This is what we call the data-centric paradigm of computing. Of course, here the bottleneck is no longer just pure compute power, although it appears so when we use so much GPUs. But that is not actually the bottleneck. The bottleneck rather is at the storage and IO interface. Okay, the ability to move and process these large amounts of data very quickly and efficiently. Okay, so it's a question of latency and also of power. And this shift is what explains why memory and storage technologies are now at the heart of modern computing challenges. Of course, the reason why we have data-centric computing was also the availability of big data through advances in memory and storage technology, something that we have discussed in detail. But now that has become the heart or the area that you want to solve when you look at modern computing challenges. Okay, so why are AI, ML, or data-driven algorithms such a big deal? It comes from the recognition that for certain, not all, certain computational tasks, even a baby's brain can really outperform a supercomputer, both in terms of power efficiency and performance. Now, as I said, this is not for all tasks. For example, when it comes to pure number crunching like arithmetic, of course, computers are unbeatable. But when it comes to pattern recognition, classification, decision making, even a baby's brain, just like I mentioned, is way more efficient. A very good example is something that we notice in daily life. So even a 2 or 3-year-old kid can look at a dog, a cat, or a person's face and immediately recognize it, even if he or she has seen it only for few times before. Not only that, even if the learning for the kid has happened in different contextual environments, such as from a different angle or from poor lighting, or if the face or the dog or cat is partially hidden, the baby does that very, very well. And it does that almost instantly, no latency, and just with very few watts of power that the brain consumes. But remember, the baby's brain is not only doing that, it is doing many other functions. Now, compare that with a supercomputer. For modern days supercomputers, to achieve the same level of classification or object recognition, you need to train these deep neural networks on millions of images running on thousands of GPUs, consumes several megawatts of power. And even then, the machine can easily get confused if you slightly distort or alter the image. For example, if you add some noise or you change the context, the supercomputer, which has been trained on so many images, gets confused. So, in essence, pattern recognition, generalization from very limited or noisy data sets, the human biological system or any biological brain is far more efficient than even the current most powerful supercomputers that human beings have built. And this is exactly why AI algorithms become very, very important, because they are trying to mimic these brain-like capabilities in machines. Okay, and at this juncture, it might be absolutely essential to clarify few terminologies which are sometimes used interchangeably. So what is this relationship between artificial intelligence, machine learning, and deep learning? You can think of them, as you can see in this figure, as 3 nested circles. So at the outermost level of the circle, we have artificial intelligence or AI. AI is really a very broad term of making machines that can mimic any form of biological behavior or intelligence. It could be anything from, simple rule-based chatbots so that it gives you a feeling that you're chatting with an actual person, self-driving car, or even mimicking how birds use the magnetic fields of the earth to navigate. So AI is really a big umbrella term. Now, inside that, we have something called machine learning or ML. Machine learning is one specific way of doing AI. Instead of giving hand-coded rules, which is generally done with computer programs in the regime of logic-driven computing, what we do in ML is you let the machine learn patterns from a big data set. For example, if we give, just from our previous example, the machine thousands of images of dogs and cats, it can now learn to classify new images. And this happens without us writing explicit rules for cats or for dogs. So ML is nothing but AI that learns from experience, a specific way of doing AI. And then within ML, we have a smaller nested loop called deep learning. Deep learning is a subset of machine learning that is inspired by the way our brains and neurons work. Here, artificial neural networks with several layers, and that is why you call the word deep, several layers, deep. This technique is behind all these breakthroughs that you see or you hear about, such as image recognition, pattern recognition, speech processing, NLP. All of this is powered by deep learning. So our focus for this course, therefore, will be to look at these deep learning neural networks. All right. So before we deep dive into AI/ML based computing, it will be very important to clarify a very common misconception that AI/ML is not a brand new field. In fact, the roots of AI go way back into 1940s, where people started thinking about how, using math and probability, you can make sense of data sets. And this was called statistical learning. So what we are seeing today is not the birth of AI, but many, many years of maturity and scaling up of ideas. Next, artificial intelligence, which was a concept which took shape in 1950s, was born, and the goal was simple. As we discussed earlier, it was to engineer intelligent systems, intelligent machines and programs which can think more like human beings. Then in 80s and 90s, machine learning started to take primary importance. Here, the approach shifted. Instead of, as we discussed, hard coding intelligence, what you started developing is algorithms such as decision trees, system vector machines, and some early neural networks, coming to current day where deep learning, which has made AI/ML computing really pervasive, came into the fold. And this is what enabled these breakthroughs in speech image processing, which is basically also we call as the AI boom that you keep hearing about. However, the actual history of AI was not that linear. Okay, so I know in this class I'm spending a little bit more time on explaining the different breakthroughs and historical aspects of AI. So you may wonder why that is the case. Why do we study history in the first place? One of my teachers once told me, you should study history, especially the history of science and technology, to understand what were the mistakes that were made earlier. And in the excitement of a field growing, you do not make the same mistakes. Not only that, it also gives you an idea or handle of what changes need to be made so that you can avoid the mistakes of the past. Just like the development of any technology, the development of AI/ML has also been a roller coaster ride. However, the first period, the early stages of AI, is what I would like to call the golden era of AI. This was roughly from 40s to 60s. Why is this golden? Because several foundational ideas that we still use in today's AI ML algorithms were already developed in this golden period of 1940s to 70s. It all began with the Macaulay-Pitts neuron model. First, let me tell you that these developments were done both by neurobiologists in understanding how your brains and individual fundamental units of brain computing, such as neurons and synapses, work. So there was a lot of development in neurobiology and also in trying to mimic this neurobiology through computer programs or through models by computer scientists or mathematicians. So it begins with the Macaulay-Pitts neuron model in 1940s. This was the first mathematical model of a neuron. It showed that you can represent neurons as simple binary thresholds with the firing of yes or no. This we will see is eventually spikes. Okay, this was the seed of trying to build artificial neural networks. Then came Hebbian learning in 1949, something that we will discuss for quite some time in this course a little bit later, because it also forms the foundations of today's spiking neural networks. Next, in 1958, Frank Rosenblatt introduced the perceptron model. This was the first real implementation of a trainable neural network. This could classify very simple patterns, and for a while people got very excited. You see the growth that this could be the panacea, or this could solve all problems, and they are a gateway to machine learning. Okay, but parallel to all this, in computer science, Alan Turing's work on Turing machines laid the theoretical foundations of the computation itself. It showed that what a machine in principle can compute or cannot compute. Okay. He also came up with something called the Turing test. We will see what the Turing test is very soon. Finally, in 16s and 70s came the breakthrough idea of backpropagation, which we still use in today's deep neural networks, which gave a practical way to train multi-layer neural networks by propagating errors backwards. Because it is such a fundamental idea, we will go into details of it very soon. Although this algorithm became popular much later, its roots go back to this so-called golden era, as I say. However, it became soon very clear that the perceptron had very severe limitations, most notably as shown by Minsky and Papert in their book called Perceptrons, that the mathematics, they gave a mathematical proof that single layer perceptrons could not even solve very basic problems, such as XOR operation, which can be done by logic gates with a very small footprint. This realization, combined with very weak computing power of that era, led to a disappointment, led to really less funding in this area, less interest in this area, and brought in the first winter of AI. After all these amazing developments, people realize maybe things are not as good as they appear. Despite these setbacks, research continued, and in 80s, it marked the second AI boom, largely thanks to something called expert systems, which were again a rule-based program designed to mimic human decision making in very, very narrow domains like medical diagnostics or maintenance, troubleshooting, etc. These systems gained a lot of industrial traction and there was a lot of corporate funding. But a deeper breakthrough also occurred during this period. The rediscovery and popularization of backpropagation algorithm by several scientists in the late 1980s. The backpropagation now was a framework which provided a very systematic way to train multi-layer neural networks, as we discussed, by propagating errors backwards. Okay, and this innovation overcame a lot of these limitations of single layer perceptrons. However, the compute power and availability of limited data sets were still stopping the unlocking of AI/ML's full potential. And even things like expert systems started to collapse because they were very functional, they're very limited, and also they had high cost. And that is why I called this period from 70s to late 80s 90s as the second winter of AI. And it was not until the 2000s that AI experienced its next big boom, where deep learning emerged as a very powerful paradigm. The early landmark moments included IBM's Deep Blue defeating the world chess champion Garry Kasparov. So Garry Kasparov is sometimes said to be the best chess player that has ever existed. And this happened in 1997, which symbolized that now machines, even for complex tasks like playing chess, can dominate human beings. Next came the showcasing of natural language processing through IBM, where they were able to beat the Jeopardy champion in 2011 through IBM's Watson supercomputer. What is Jeopardy? In normal quiz shows, you generally ask the question and you expect an answer to come from the participant. But in this interesting show called Jeopardy, what the questioner does is he gives certain hints. For example, if I say that who was for several terms the chief minister of Gujarat and then prime minister of India. So this is the question, and the answer would be, who is Narendra Modi? So the questioner is giving hints and the other person is supposed to, or the participant is to ask the question. This is the format of Jeopardy. As you can understand, it requires human intelligence, especially natural language processing skills. So this is what IBM's Watson had done. It had beaten the current Jeopardy champion. But the breakthrough moment came in 2012 when Geoffrey Hinton's team used deep neural networks to win the so-called ImageNet competition by a huge margin. And this is where all these developments of Google's self-driven car or your DeepMind's AlphaGo beating Go champion, something that we will see in detail, ChatGPT, etc., what we are now using very pervasively in our lives, came into the fore. Okay. However, it is very important to understand that the current generation of AI ML may look very exciting, but we should look back and see there have been periods, lot of excitement, but there were also these winter periods. Okay. And this brings us to two very important questions, which we will try to answer. Okay. First is, why was there a lull period? Why was there a gap in the period where there were a lot of ideas that were generated, but execution took quite some time? It took almost, you can say, 30 to 40 years. What changed after 2000 that all these ideas that were earlier developed could finally be used for practical systems? This is the first question that we are going to ask. What is the reason for the lull period? The next question we will ask is, if these lull periods of lack of excitement and lack of development happened earlier, can it happen now again? Will AI, as we expect, keep going up, as I have indicated in this green line? Or can there also be periods or reason for which the excitement of AI/ML can come down? And this is all incumbent upon us. We have to look at what are the real sustainability challenges, especially from the perspective of hardware, in running these AI/ML algorithms. If we do a closer deep dive, we will come to appreciate that although AI/ML algorithms have developed quite a lot, the underlying hardware infrastructure is still in a very immature state. And this is what is causing unsustainable amounts of power consumption. Why is that the case? We will start looking at that from the next class, where we will look at a typical task in AI/ML algorithms and how you take inspiration from biology to make these artificial neural networks, and why these artificial neural networks are able to solve these complex computational pattern recognition tasks. Okay, so let us conclude our lecture over here. In the next class, we will do a deep dive into what are ML tasks and the understanding of deep neural networks. Thank you for your attention. See you in the next class.